Yeah. All right. So I think I'm recording now. So we are going over the last page of your notes, which I think yours just says practice makes you proficient, since we don't have any quizzes. But the 4 types of intermolecular forces were ionic, H-bond, dipole, and the last one, I'm calling it London, but you can also call it, in the past, a lot of students called it ID, which was for induced dipole. It's also called in some books dispersion forces, and also it was also known as van der Waals forces. So I had originally learned it in biology way back as van der Waals forces. So ionic, I think you all know, metal, non-metal. H-bond, you were right, Aaron, that is NOF. So nitrogen, oxygen, or fluorine, if you see any of those, that's the little gnome's hat. So when a hydrogen is attached to an N, O, or F, you have an H bond. And so in our examples over here, it becomes something that you should just see. There's actually only one of them, and it's the NH2. So when you see the hydrogen on the nitrogen, that is an H bond. And these are written in the order of strong to weak. I also realized when I was looking at this page, these are actually the same examples I did in the lecture. I must have just copied and pasted, and then I meant to change them, and I never did, but I figured you all printed it already, so we'll just go with it. It's good practice still. So if you see nitrogen on the hydrogen, over here, the hydrogen again, the carbon is in between them, so that is not an H bond. And also here, this one with the oxygen, these hydrogens are on the carbons. The oxygen doesn't have any hydrogen on it, so there's no other H bond here. So H bond is a really strong dipole. It just means there's such a pull by the N, O, or F, because they're the most electronegative. All right, then our last two, the dipole is just something that's polar, and London is anytime you have something that's non-polar. And that's where you're just looking, it's a very momentary dispersion of the electrons that creates this. So like this top one, they're both non-polar. So when you see only carbons and hydrogens, nothing else, that is nonpolar. And then silicon on the periodic table, it is right below carbon. So the silicon surrounded by 4 are the same thing. So even though the fluorines pool, they cancel each other out. And so this is back to the question you're asking me earlier. If they're both nonpolar, you were going to tell me the type of force, which we would say is London. So on the worksheet, I specifically asked, name the intermolecular force. And this is something I was talking about in the lecture. For like 10 years, I was calling them correctly interparticular forces, because ionic is technically not a molecule. And you can also have where you have just atoms like argon that you're comparing, but it never caught on. And so I now go by intermolecular forces again. All right, if they're both London, you pick always the bigger one, so larger surface area. You only look at surface area for London. For the other ones, you're looking at the polarity. And so on B, the nitrogen is pooling, so this is definitely polar, so we say dipole versus H-bond, and the H-bond always beats the dipole. It's a very strong dipole. Now a question, Aaron had looked at his study set, and on the study set, the second question runs into an interesting thing. There is something on there that is non-polar, and it ends up being the strongest one just because it's such a large size. And I avoid questions like that on a test situation unless I would ask, why could this be much higher? And it would be because even though it's non-polar, once you get a really large surface area, it will overcome, it will make it, it will actually knock it up to above the H bond. But you have to have a pretty large surface area. All right, on C, the ionic is going to win, but I wanted to go through this one again. So if you see a carbon, carbon's going to have 4 things around it, and unless they're all 4 the same, something's going to be pooling. So you don't have to draw it. I'm just going to draw it to remind you. So the carbon makes 4 bonds. It loves to make 4 bonds. So the chlorine makes it different. And so this is going to have a dipole, but ionic is definitely going to beat the dipole. Now, something I did not talk about the other day, oh, we'll get to it when we do we'll look at the lab. I have a page for that. All right, so on D, this one you see only carbons and hydrogens, so London or induced dipole. You can also just write ID, capital ID for induced dipole, or you can write London. And the other one, you have the oxygen, but there is no hydrogen on the oxygen. So you specifically need the hydrogen on the oxygen. So this is a dipole. And so the dipole is going to be stronger. All right, and then the last one, this is kind of back to the question you were asking earlier, Erin. It is all carbons and hydrogens. And since it's only carbons and hydrogens, they're both nonpolar, or they're both induced dipole, or both London. And so the question Erin said is to look at surface area, you look at molecular weight. That's a simple way of saying it, but you're really looking at which one is covering more surface. In this case, they both have 4 carbons. And so the first one is covering more surface area because it's more linear. If we drew this, how they would really look, this would be a zigzag. Each corner is a carbon. And this one would actually just look like this. So our first one would be covering more surface area. And that surface area means if you have more surface, there's more area for this dispersion to happen over, which creates enough surface for it to be stronger. So any questions on that number 1? All right, so then the second question on that page has one of these charts, and it asks which compound's the most volatile. So these charts, the temperature, it will be labeled for you. And the line here, this is something we'll be talking about Tuesday. The lecture next week is on gas laws. And this will really emphasize it, that 760 is standard pressure. So that's something in the homework, you'll have one of these charts and it will ask something about normal boiling point or standard pressure. But what's happening is that every time it hits one of the lines, that's the boiling point. And so at each pressure, they each have a different boiling point, because boiling point is when the pressure above the liquid becomes the same as the atmospheric pressure. And so the bubbles are escaping their confines of the intermolecular forces. So once they get enough jiggles, they overcome that attraction. So the most volatile one is going to be the weakest one, which would be the one that's furthest to the left, which is going to be the pentane. So the most volatile, we would say, is the pentane. It has the lowest boiling point of the 3. So it's evaporating the fastest. So volatility, again, was how fast it evaporates. So ease of evaporation, which again is how easily it escapes. So you can say evaporation or escapes the liquids IMFs. So the big difference between liquids and gases is the intermolecular forces. I'm doing these lectures backwards. I usually do gases before liquids, and I kind of actually like this order better. So when we get to gases, you'll already have the idea of intermolecular forces, and that's what makes a gas special, is it has escaped those attractions. And so something that has very weak intermolecular forces is going to escape easier. All right, so on B, which one has the strongest? Well, it's going to be the opposite answer. And so it's going to be the one that is the furthest to the right. So in this case, it's the water. So the H2O. So the strongest attraction means the strongest IMF. So the IMFs, again, are always just an attraction. They're electrostatic. I forgot to mention that the other day. So these are all electrostatic in nature. Ionic H-bond dipole in London. So there, and all electrostatic means is positive and negative attract. So you have this attraction. There's, in nature, there's, this is probably all different now because things change in the world very rapidly. There were 4 forces a year ago or 2 years ago. I think there's 9 forces now, but the 4 forces were gravity, so what pulls 2 masses together, right? The electrostatic, which is what chemistry is based off of, the positive and negative, and then the 2 forces in the nucleus, so the strong and the weak force, which are completely mythical from what I've read, that to be able to explain how the nucleus can be held together, they created these forces. And they made the math, and the math proves that they're right, except they created the math too. And so a lot of these new forces are kind of like that. It's to explain why their math equations work. So you can become one of those people who makes the math equations work. All right. So anyway, there's always, it's a pool of positives and negatives, and so the stronger they are. The one in the middle here, the tetrachloromethane, it's going to just always stay in the middle. It's never going to win any of these contests. So the most viscous. So this is a question of the day. Does anybody remember what viscosity was? I don't expect that you did.
Stickiness.
Yeah, I actually like that word. So how sticky it is. The technical definition is resistance to flow. So it's not flowing. So it's sticky or not flowing. Liquids love to flow. So something that's going to have really strong attractions is going to be getting stuck. And so that would be, which is really interesting here. We don't usually think of H2O as being viscous because it's not, but compared to the other two, it would be the most viscous. All right, on D, it just wants the normal boiling point. And on this graph, it's nice. It already had the line for you and wrote the number. So for the tetrachloromethane, it is 76.5. I would say probably the biggest mistake students make is they forget to put units with numbers. So again, we're back into starting to do math again after doing all that stuff with Lewis structures. So just putting a unit with it. All right, on E, so this is just reading the graph. So we would find 30 degrees, which is halfway in between 20 and 40. And we're going to pentane, so you would just come up. I don't know if I have a ruler on my other class notes. So we'd just come up, we'd find that we're somewhere around here, and we're probably like 450, 470. I'm gonna go with 450-ish. So ish just means approximately. So somewhere between 450 and 500. Now, if you give me an answer of 450, you're gonna lose part credit because you need a unit. And it tells us our unit here, millimeters of mercury. Again, next week we're going to do gas laws, and we will talk about pressure and what pressure is, and look at the units of pressure, which are interesting. Millimeters of mercury would be one. All right, and then the last one, what is the state of matter of pentane? So we just have to find that point on the graph, which is up here. My star would be 650, and 500. These, again, are vapor pressure curves. And what happens, the line is the boiling point at different pressures. So again, I talked about if you were climbing a mountain, this would be climbing down the mountain and going to sea level. So as you go up a mountain, you'd have to get to the top of Mount Everest, you'd be around here at 200. So this is where it boils, is this line. So pentane has already become a gas because it has already crossed over. The tetrachloromethane and the water at that point would still be a liquid because they would still be on the other side of the line. All right, so questions with that. Your worksheet is very similar to this page, so this should help you with the worksheet. All right, so go ahead.
I was wondering, do you prefer for the units for vapor pressure torr or
so they are the same thing, and that's what we're going to talk about on Tuesday. They are, those two units are interchangeable. So his question was torr or millimeters of mercury. Sorry, I anticipated your question for you. Torr and millimeters of mercury are actually the exact same unit. And so I usually change it to torr because it's easier to write. And the abbreviation for torr is just a little t. So you'll see me doing that when we get into gas laws. Now, those are actually not units that are used scientifically very much, but they are used in the lab because you can measure it with if you have mercury, which labs don't have anymore. So in physics, they use kilopascals. We'll be using atmospheres, ATMs. So, all right. So I just went with, so going back to your question though, Erin, I went with how the graph was labeled. So since this graph was labeled as millimeters of mercury, and the graph we did the other day, sorry, is here, and this one was labeled as torr. That's why. So and you might have one on your homework. If it's in ATMs, just keep it, whatever the units are, just go with the units of the graph. All right. When we get to gas laws, that won't be our motto, but we'll worry about that next week. All right. So drawing a hydrogen bond, you have these intermolecular forces, you always have to have two molecules, and they could be the same or they could be different. So on this question, I want you to draw one NH3, and it doesn't matter how you draw it, and one H2O. The trick is, it is nice to show the bend. The nitrogen and the oxygen are the negative areas, so they would have those partial negatives, and the hydrogens are the positives. So the nitrogen is going to be attracted to the hydrogen on the oxygen, or the hydrogen on the nitrogen is attracted to the oxygen. Now, there's a question in your homework I want to do, but a reminder, these are attractions, so we always show them as dots. When we show a bond, we show them as a line. So there's our H2O. There is a question that is on the homework, and I actually just realized it's the same question on your worksheet, but it's all right. I want to make sure you guys get this. And I usually go over it in class, so it has you do H bonds with this molecule. And so a couple of mistakes happen. About half of you only draw one molecule, and you can't do an H bond to yourself. So you have to have a second molecule. And the mistake students will make is, and I'm going to make a couple mistakes, so I should probably see if I have a pencil, since I do. So I'm going to do this wrong first. So you have to draw two molecules. And the mistake students will make, because you're going to have to do one of these on the exam, this is one of the big points of the class. This is, H bond does not mean between hydrogens. An H bond does involve a hydrogen, and the other misnomer is it's not actually a bond, it is just an attraction. So this is wrong. You would not draw it between the hydrogens. The other mistake is you can't do any hydrogen to oxygen. So you're like, oh, I get it, that the oxygen is the negative, and so this hydrogen that's attracted, that is attached to the carbon, is not polar. So it has to be a hydrogen that's being pulled. And so it can't just be any hydrogen. It has to be a hydrogen that's very electronegative. So it would have to be these two parts of the molecule would have the attraction. So from this hydrogen to this oxygen, or this oxygen to this hydrogen, whichever way you want to look at it. But this hydrogen has a positive. The hydrogens attached to carbon will never hydrogen bond, because carbon-hydrogen is nonpolar, and you need the NOF to make this work. And again, you'll see this question on your homework. It goes back to all those questions we were doing on the first 3 weeks of the term. And it kept asking, what's the most polar bond? And it was the idea that the OH was an extremely polar bond, and that makes it very special. And in biochemistry and organic chemistry, it adds another dimension of special. All right, question 4. Yeah, all right. The question says, so if the IMF decreases, so meaning it's weaker, so the weaker the IMF, the boiling point is going to go down, because you don't need as many jiggles to overcome it. So boiling point is how many jiggles you need. Heat of vaporization is a similar idea, but it's just the units. Heat of vaporization, we're measuring in joules and kilojoules. So that would also go down. You don't need jiggles. They're not the same thing. When you take physics, or if you go to higher level classes, you can worry about that. For vapor pressure would definitely go up. So if something has weak intermolecular forces, more of it is going to escape. So weaker ones are going to be easier to escape the IMF. And so whenever I say that they escape, it means that they become a gas. So liquid to a gas. And that's what vapor pressure is measuring, is how much has become a gas. What other ones are going to also be easier to do when they're weaker? Volatility. So volatility is measuring how easy it is for something to evaporate. So the very last one will also go up. And the rate of evaporation and volatility are really, in my opinion, or in the simplicity of my mind, they're really the same thing. So vapor pressure and volatility, they're gonna, if you have weaker intermolecular forces, they're gonna be higher. Boiling point, heat of vaporization, and viscosity, they're all gonna be lower. There is one missing from this, and that is the extra credit bonus that I posted last night. There are different challenges that you can try. You can watch it. I think it's only like 15-minute video, and you can, yeah. It's to bring your inner child out. I actually listened to a talk today, and they said that's what we all need. But surface tension is the attraction at the surface of liquids, and water has a very high one because of the H bonds, and it allows you to do some really cool tricks with it. And so I posted a video with that. And then the other thing I wanted to mention to you guys, because I was saying next week, I'm going to do the lecture next week the same I did this week on Tuesday. I can just do it after the office hours at 7, and I'll just do it in my other room. And we're going to fix the lighting in there, so hopefully it will work better. But I decided, instead of me doing demos, I'm going to offer, you guys are going to do the demos. So there's so many gas law demos that you can do at home. And so that's going to be an assignment. Everybody in the class is going to have to videotape themselves doing a gas law demo. And that's going to be part of your next lab like 6 or whatever, 5. I don't even know what week we're on. All right. So question 5 is the one you were asking me about, Erin. And I actually had worked it out so I could look super smart. But this is the heating curve. And so you always have these 5 steps. This part here is flat, and this part here is flat. And then these are diagonals that are just connecting it. So the lowest diagonal, so it's kind of like a slanted staircase, is solid, liquid, gas. And then the first flat line is called the heat of fusion. So it's the amount of heat to change a liquid to a solid. And the top flat line is the heat of vaporization. So on your homework, you get to draw 2 of these. You actually don't have to draw the whole thing, but I give you enough information. These numbers are always going to be given to you because it's different for each one. Like this is specifically something that's only found in Yetis. Every year we get to this quiz is usually week 5. Like I said, I switch the gas laws and the liquids. Gas laws tend to be pretty easy, and so students, I put them after this, because in the 5th week, what I have found, no matter what's going on, is everybody starts getting a little tired, because you can't see the end of the tunnel yet, because we haven't quite reached the halfway point. And so usually this is week 5, and everybody's really grumpy and complaining. So I moved it forward, so nobody's too grumpy and complaining, because we're all in isolation. So even if you are grumpy and complaining, I can just end the meeting and send you all home, and I have like this master power of just kicking you all out of class whenever I want. If you want, I'm going to label my axes on here, but when you look at my answer key for the homework, I often don't show the axes on these. The bottom is just the amount of heat added. So as you're adding more and more heat, the solid is jiggling. Everything jiggles. So the heat is going to make it jiggle and wiggle and giggle. You're going to hear me do that like for the next 4 weeks, because everything we talk about. So you get jiggles and wiggles and giggles. And usually when we're in class, everybody's giggling or wiggling or jiggling in their seat. So it's really fun. All right. So it changes. So the solid suddenly no longer has its pattern, and it becomes a liquid. And this flat line here, again, both states of matter exist, the solid and the liquid, until it gets to this corner, and then it's completely a liquid. And then here it's jiggling, it's still a liquid, it's just flowing more, and eventually it gets to a point where some of it's starting to escape, and more escapes. And then when we get to this corner, it's completely all dispersed. This graph, this side, the x-axis, sorry, the y-axis is the temperature, the x-axis is heat. And that's important because it can tell us, it tells us the melting point is the first flat line, the heat of fusion, and the second flat line up here is the boiling point, which is 230 degrees. And the melting point is -30. So the challenge most of the students have is that negative. So that's drawing it. They always look the same. The thing that's going to be different is the numbers along the side. The heat of vaporization, I drew this incorrectly. The heat of vaporization is always much larger. So if you look at these numbers, my flat line here, the top one should have been larger, but those are all minor things. We do the best we can. And that is because heat of vaporization, the difference between a liquid and a gas is very significant, because the gases have escaped the intermolecular forces. So you need a lot of heat in this area, in this flat line, to overcome all those intermolecular forces completely, so now they disperse. The difference between a solid and liquid is just the pattern. So you're just jiggling some, but you usually don't need much heat to change something from a solid to a liquid. All right, so for the math, this is the step that students struggle with often because it's different every time. You could have 2 steps, which is what we're going to have for this one. You could have 3 steps, you could have all 5 steps, but they are steps. They end up being separate steps. I'm going to show them as separate steps. You can do it as one setup. Just make sure it's labeled. So we're solving for heat, which is symbolized as Q, and the temperature we're starting at is -50. So if the melting point's -30, it means we're starting down here in the solid. I think the example I did the other day, I don't remember now, because I also did the homework and the worksheet, but you're going to be at different places. So you want to figure out your starting point and your ending point. And the question just wants to know, we want to completely liquefy it. So we're not ending up in this part anywhere. We're just ending up right here at this corner. So we're going to have 2 steps. We're going to change the solid. We're going to melt the solid. And then we have to go through the Q of fusion, so the delta H of fusion. And so label your 2 steps here. And there's 2 different ways you can think about it. I just look at it as unit conversions, so the factor label. And those of you, which is most of you, had me, or if you had Bernadette, you should be pretty good with factor label. Or Alina, I know she had Dr. Whitman, and she does a lot with factor label. So if you go up here for the solid, we know this piece of information, that the specific heat of the solid was 1 joule per gram degree Celsius. And we're trying to solve for joules or kilojoules. So we have to get rid of the grams. So you're going to always be multiplying by the mass. And we have to multiply by the temperature to get rid of the Celsius. The trick is it's always the change in temperature. The other way to think of it is this is mass times C times change in temperature, which was a formula we learned. I'm not a huge fan of that formula, but you can also look at it that way. And the reason I'm not a huge fan of it, it doesn't work for our second step. But the temperature is the change from -50 to -30. So I think it's easier to do it logically in your head. The change from -50 to -30 is 20 degrees. And then you would punch it in, and it would be 2,000 joules. This was a question, and Janae asked the other day. I prefer to go to kilojoules. I just like working with smaller numbers, so I always change them to kilojoules. So you would divide by, you would of course show the step 1,000 joules to a kilojoule. Because what I found is students change it in a funky way. You can leave it in joules. It's just the 2 steps have to have the same unit. So for fusion, we go up here and we would want this step. And the delta H of fusion is this number, the 10 kilojoules per mole. We have to get rid of the mole. So there's 500 grams per mole. You would use the periodic table on the homework. I think it's silver and NH3 are the problems. And then we use, to get rid of the grams, we use the mass. And you get, again, 2 kilojoules, and you add the 2 numbers together. And again, sometimes it's 3 steps, sometimes it's 4 steps, sometimes it's just 2 steps. But so Erin, your question earlier, I think the diagram is helpful because you can figure out where you are in the diagram. But I will tell you, these for some reason are frustrating for a lot of students. And I think my feeling, I actually like them. I think they're really fun. And I know it's not just me, because it's something that my colleagues also say, that we all struggle with teaching this because students always have trouble. I think it has more to do with we're like in the 4th, 5th week of the term, people start getting tired. You have exams in other classes. In the spring, the weather starts getting nice and we want to go outside. But do you guys have questions with this? There are 2 more of these in the homework set, and I did post the answer key and I wrote out my steps.
I do have a question.
Go ahead.
I was wondering why, I don't know if this is just showing 2 different ways. I was wondering for the first one, why don't we go down to 500 grams to 1 mole? And then,
oh, because there's no moles in this line.
Yeah.
There's no mention of moles. So in the homework, that's a really good question, Erin. So when you do the study set, one of the questions, all of these are per mole. They're molar specific heats. And so then you would have to. So if the number given for the graph up here involves per mole instead of per gram, you will have to change your moles to grams, and then you can cancel the grams out. But because this step here, there's no moles, I didn't have to use the molar mass at all.
Okay, so so you're saying that the molar mass doesn't apply to the fusion part, or wait, oh, I see. I might not be reading the question fully. Let's see. I think I'm getting what you're saying.
My advice to everybody is just watch the units. So if you make your units cancel, that will tell you what you need to do. And the unit you're trying to get to is joules or kilojoules. When you add them together, they have to be the same unit. And I just prefer to go to kilojoules. If you kept it in joules, you would have had 4,000 joules. So, yeah. And again, there's 2 on the study set because usually this is the biggest question students have. And I think it's just, it's different because it's stepwise. But that is one of the wonderful things with unit conversions. And like earlier, we were talking about physics. And I've told you guys that story before that, you know, sometimes we like, it's the same like when we do gas laws. We're going to do it all with formulas, but you can always go back to unit conversions if you get stuck and just get the units to cancel out, and it always works beautifully. All right, do you guys have other questions? If not, I wanted to go over one thing about the lab, which will probably take another maybe 10 minutes. And yeah, that's me. I want to talk about the lab. See, you don't have this page in your notes. So as I mentioned, the week, what week are we in? Lab, we're in week 4. So lab 4 is going to have 2 parts. So the one part is kitchen chemistry. You're going to make milk. You're going to make cheese, sorry. And that has instructions. And actually, I'm going to post a video that goes with that because the video gives you all the answers to the post lab if you want to watch it. It also might give you an idea for your topic if you're still looking for some ideas. And it also talks about why you shouldn't eat cheese because it's really not good for us. And then the other part talks about different types of solids. And so it's very different. This one, the solid types, it's the gnomes, again, did the lab for you, and they filled out a data table for you. And so you just go through, they're gnomes, and gnomes are mischievous. They're just misunderstood. They didn't fill out the whole table. So you're gonna have to fill out the rest of the table just based on your comment, well, from reading the lab. But there's, so we're gonna look at the solid types for a few minutes here. You can have ionic, you can have metallic. And I'm going to zoom this so it's higher. Here we go. All right. You can have what is nonpolar molecular. You can have polar molecular. So these kind of go together, but they are separate because. And then there's a last one that's really special that is called macromolecular. And macromolecular, it's all one molecule. So the difference between molecular and the lab has like 2 pages of typed out, but sometimes hearing it then reading it makes some sense. The macromolecular, the whole thing is one huge molecule. And the example of this, I have some. A diamond, I don't have any diamonds, but I have, oh, I think they're in the kitchen. That's a bummer. So when we were in Nepal, Pimba went off somewhere. He was trying to take me and Joey there, but I couldn't make it. I wasn't doing well at the altitude. But he came back with all these quartz crystals. And so quartz crystal, they're macromolecules. So that would be silicon dioxide. So the whole thing, or diamond, graphite is macromolecular. And so this is actually here. This is a picture of a diamond. I think in your lab I have a picture there too. But the whole thing is all covalent bonds. There's no attractive forces anywhere in it. And so that makes it very different from these two categories. So it's all covalent bonds. And that's why diamond, I'm pretty sure you all know about diamond, it's the hardest substance. And that's because it's all covalent. There's no IMFs. So again, it's like if you were an octopus and you have everything's connected. It can't be taken apart. Silicon dioxide is sand or quartz or stuff like that. And so it's all connected to each other. These guys here, the nonpolar and the polar, they have IMFs. And so what you would do in lab, if we were doing this lab, one of the ways you can distinguish these 5 categories is you actually melt them. So you don't get to work with Bunsen burners, the gnomes do. But you can wear your goggles while you do the lab, fill out the data table fictitiously, that these two, the nonpolar and the polar, have low melting points. They melt pretty much in 2 seconds. Like you have them in the test tube, and as soon as you put the test tube by the Bunsen burner, it melts. Whereas the macromolecular, you hold the test tube for 3 minutes over the Bunsen burner, nothing's going to happen. There's no way you're going to melt a diamond or sand in with a Bunsen burner. And so the question that always comes up is about the IMFs. The students will say, but you said hydrogen bonds are really strong. There's no comparison. A hydrogen bond is like a zipper. You can overcome it with jiggles. And so melting just means we're jiggling. Ionic and metallic, they just have medium melting points. They do melt, they just don't melt immediately. You guys actually know how you can tell something's a metal, because metals do something nothing else does, which is they conduct as a solid. And the lab has like 1 or 2 sentences. I don't know if you remember way back, my very first lecture in 221, I talked about that plum pudding model where electrons flow. I was trying to see if I had a picture of it, but I don't. But the electrons, the idea of metals is you have unbounded nuclei. And so these would be these nuclei. So you have these sea of positive islands, and the electrons can actually just flow in between them. And so they conduct as a solid. And that's how you can tell you have a metal. Nothing else will conduct as a solid. Ionic does conduct, but they conduct when they're aqueous. So this is kind of a segue where we're going in 2 weeks, which is we finally come and study aqueous. And aqueous means it's in water. So as a solid, if you try to see if your sodium chloride in your salt shaker conducts electricity, it's not going to conduct as a solid, because the sodiums and chlorides, it's the lab you guys were all doing tonight, the sodiums and chlorides are all stuck in their rigid shape, right? All those balls you had to draw that some of you drew so beautifully, you all drew beautifully. But once you put it in water, the water pulls the ions apart, and now the ions are swimming around, and ions have a charge. And so once you have free ions, you will conduct electricity. And so that's what distinguishes these two from everything else. The molecular ones, whether it's polar, nonpolar, or macro, they cannot conduct. They have no charges. So a dipole is just an area positivity, but that does not allow it to conduct. There is a wee exception to this. Well, the big exception is graphite and graphene, which is like the future of our cell phones and stuff. So graphite, I talk about it in the lab. It's actually the story in my lab is about graphite. But graphite is sheets of carbon. And so those sheets can actually slide past each other, and that allows it to conduct. But anyway, so that's the one lab. The one lab is about these 5 solid types and has a data table that is partially filled in. It has 5 known compounds, and based on the formula, you can figure out what category and what's going to happen. And then it has 5 unknowns that the gnomes filled in, and then you just have to give your reasoning. And so when you give your reasoning, like for ionic, you would just say it conducts aqueous. For metallic, it conducts as a solid. And then Joey, my Joey, did the post-lab question, and he did not complete it. And so actually the gnomes didn't complete it. So you just have to tell them what more tests they have to do to distinguish each one. And I just realized I didn't finish. So polar and non-polar, to distinguish them, they're going to both have a low melting point. And the way you distinguish them is actually a comment several of you have made, is these are, the polar ones are hydrophilic. I've made it several times during the term. So they love water. So they're going to be water soluble. So all you do is see if it dissolves in water, and that will put it as polar molecular. And non-polar will be hydrophobic, so it won't dissolve in water. Because something dissolves in water, though, doesn't mean it's polar, because ionic also dissolves. So there's usually 2 tests you have to do to differentiate, you know, one test will eliminate certain things, and the second test will pinpoint it. But anyway, that's all I got. And so I'm going to end my, I have to figure out how to end my recording. Maybe I